Welcome to the third lecture of the second week, the third lecture on logical agents, and by this also the last of the lectures on the logical or the classical logical agents. Tomorrow I would extend the idea of logical agents by notions of uncertainty and vague information, because that's obviously something you have very often when you have sensoric information and when you deal with problems in the real world. But today still we are staying in the paradigm of symbolic logic, classical logic with clearly defined truth values, and but now we turn to a very specific part of logics, and that is the computational part of it. I spoke a lot about yesterday about the theoretical properties of certain algorithms. So is it possible for a certain problem to always find an algorithm, these kind of things. And I now really want to turn to the practical side of logics in AI, and that is the automated reasoning. So that you have some knowledge base and you want to check for some entailments. And the big question is, how can we make sure that our algorithms find exactly the right answers? What kind of algorithm can do that in an efficient way? So in the definition of what a logic is, a formal system that has a clearly defined syntax, so which are the well-formed formulae, the semantics, what is the meaning of those well-formed formulae. We now are at the third part, which is how can we calculate this meaning if we have a knowledge base and formulae? How can we assign the semantic values to it by just some algorithmic components? So this is a lot about algorithms today. I will briefly recap the semantics. That's part one, because for the third part of the lecture today, the search for the models, we need to be very clear about this notion of model again. Then I will talk about a specific case of propositional logic and subsolving that you need for the final assignment, for the knowledge-based agent that you're implementing yourself. And I also want to include some ideas of resolution and rule-based reasoning as a different paradigm to get to the results of your automatic reasoning process. So let's quickly get into the notion of semantics again. We've seen that. We're now talking about semantics of propositional logic, so we're moving one step down. We don't do reasoning in first-order logic today, because that's a more complicated issue that one really would have to devote on an entire lecture on. We are now just staying with the propositional paradigm and look at different ways of doing this kind of reasoning. And the first one is based on the notion of the model and the interpretation, because we now try to mimic what the semantics do in terms of defining our notions of truth and entailment in some kind of arithmetic calculation that our computer does. And for this, these notions are very important. The notion of an interpretation that assigns some meaning to the individual symbols of my language and then extend this to the overall sentences. And then the second thing is that from all those possible interpretations, so all the views we have of the world, we call those that satisfy all the defining knowledge in the axioms of our knowledge base, we call those the models of the world. So basically, the models are those interpretations that are consistent with my view of the world as specified in the knowledge base. And based on this notion of model, we are now also looking into algorithms to actually tell us whether things follow from our languages, specifications, our knowledge bases, or not. And I want to go back the step of the Wumpus word and the example that we talked about with this reasoning that we did, this entailment that we talked about, whether or not specific fields in the field contain pits or not. And So the question was, can we derive anything about the existence of a pit in one of the three fields where we have a question mark, given the following information, and the information that in 1.1 nothing was detected, no breeze and no stunk. And when we move to the right, we sense a breeze. So that's all the information our agent has. And the question is now, what can we say about the situation about a pit in these three places? And as I showed you, and I will also show it in this next slide, there are 8 different ways of assigning whether there is a pit in this place, in these 3 places or not. And these are those 8 different interpretations that are just consistent with the knowledge that we have nothing here, a breeze here, and then it's about assigning values to those 3 fields, and we have either a pit here, or a pit here, or a pit here, or a pit. So these are the 3 places to put just one pit. This is no pit. These are the possibilities to put 2 pits on the field, and this is the possibility to put 3 pits on these 5 fields. Yes, you have a point? That is something we are going to derive from. So we are going to show you that this is not consistent with our worldview, because the knowledge we have, and I just explained it in the slide before, tells us that this is not acceptable with the knowledge of our model, of our knowledge base. In other words, this world is not a model. So if you go to the models that are consistent with our knowledge base, we are only looking at those 3 at the left-hand side. Yeah? So this is simplification. And if you really want to do this properly, we have to talk about the following propositions, namely, there is a breeze in 1.1, there's a breeze in 2.1, there is a pit in 1.1, a pit in 1.2, a pit, and so forth. So these are all our variables, and they can be true or false, and we can just enumerate all those possible situations. So if you want to enumerate those, you start with all the falses, or you start with all the truths, and then you just switch one of the values, and you get, in the end, you get 2 to the power of n in the number of variables rows in your truth table, as most of you have already seen. And then the question is now, which of those interpretations is now consistent with our assumptions, our knowledge about the game? And basically in this case, there are only 3 of them, namely, there is no breeze in 1.1, there is a breeze in 2.1, and then there is a pit in 3.1. And basically, you can calculate each of those rows, the truth values for the knowledge base, you can calculate by simply applying the semantics of the operators and the basic assumptions of the values for your assignments of your variables. Yeah? So these 3 rows that we have here, these 3, are the only ones where the knowledge base is true, and these are the ones that we call our models. Let me see where the example is. So these are the 3 in some graphical representation to make it more intuitive, which one we are talking about. So these 3 images stand for these 3 rows. I just more intuitive ways of looking at those rows of assignments of values to our variables. And then, as I said, the definition of entailment is whether something is true in all the models of the ontology, and then it is entailed. So what we have to do is look at these 3 models of of our knowledge base and check whether a certain fact is true in all of those. It can be true in more states, but it can't be true in fewer or states where models of the knowledge base, it has to be true in all of them. That was the notion of attainment. The knowledge base entails a formula alpha if alpha follows from the information in the knowledge base in intuitive definition. And formally, this means that alpha must hold in all the models or worlds where the knowledge base is true. And the example that I showed you on Tuesday, I believe, or Monday maybe, was the question of is the state 1, 2 safe, which is this state down here. And then you basically just have to check whether the knowledge base models are a subset of all the models in which your formula is true. Because then obviously for all of the models in that model your knowledge base, this fact is also true. And so it is about this state. The question was, is that a state? And all of those are do not make this statement true. So in none of those 4, this one is true, because there is a pit in 1, 2. There is one which is safe, which is not a model, but we don't care, as long as all the models of the knowledge base have the property that 1, 2 is safe. And then we have the notion of attainment, that the knowledge base entails the fact that 1, 2 is safe. And the other example is that if you look at all the states in which 2, 2 is safe, then this would be those 4, the blue ones. And you see that there are 2 models, namely this model, these 2 models here, for which the property that A2, alpha 2 is 2, 2 does not hold. Is safe. That 2, 2 is safe does not hold. Yeah? So it's a very, very simple algorithm that we can apply here, namely just check for all the interpretations that make alpha 2 true. Look for them and check whether they are a superset of the models of the knowledge base. Or the other way around, just check for all the models of your knowledge base in this table whether alpha 1 is also true. And this was the first example. In all of these 3 models, alpha 1 is true. So we know that alpha 1 is entailed. What does it mean to think of it in this way? It means basically that we've now turned the entailment problem into a very, very simple algorithmic solution, namely search for all the models and check in all the models whether alpha 1 holds or not. And based on this notion of entailment, as I've already said, that they are strongly related to notions like satisfiability or validity. So these are more definitions, and these are just things that you need to learn by heart and understand what it means. Namely, a sentence is entailed in a knowledge base if it is true in all the models of the knowledge base. A sentence is valid if it's true in all the models. It's satisfiable if there is a model that makes it true, and it's unsatisfiable if there's no such model. So this is simply sort of understanding enough and then assigning the terms, the necessary terms to it. You need to be able to tell me what entailment is, what validity is, what satisfiability is, and what unsatisfiability is. And all those notions can be sort of reduced to one and each other in some of the languages, and in both the language we're talking about and in propositional logic. So what we're looking for is the notion here in reasoning of proving satisfiability. So we are looking for a calculus, an algorithm for inference, that tells us whether a certain fact follows from a knowledge base. So the question is, if this is an abbreviation for, we can calculate whether f is true or false with respect to our knowledge base, is that exactly the same as all the formulae that are semantically entailed by our knowledge base. Now I have these algorithms, which I usually abbreviate with this notion of nail or whatever it's so normally it's written like this. So this is I write it down here so that it's also visible on the video. So this is the calculus, and this is the semantics. And it basically means if I have a knowledge base and I prove that Formula 5 follows, that should be exactly the same as the semantics that I define whether something is entailed according to our definition of the model theory. And now we're looking for algorithms. And we have two different, or many different types of algorithms. We have the algorithm that tells us that whenever I have something that is entailed, it is found. That is the notion of completeness. Then the other way around is, whenever my prover says this formula is entailed, it really is entailed. Yeah? So if my algorithm tells me this, then this must hold. That's the notion of soundness. So it basically is the correctness of the algorithm that it always gives correct answers. It might not give all the correct answers. In some cases, if your algorithm isn't that good, or in some cases it's impossible to do it completely. But the other direction is also interesting. So the question is, if I know that something is entailed, so should logically follow, does my algorithm also give it back? And that's the notion of completeness. These are two very important parts of this process, because if I know that an algorithm is sound and complete, I'm almost having a decision procedure. So a procedure that always tells me the correct and only the correct things. It's not yet a full decision procedure because I might lacking the property of termination. So it might be that my algorithm gives all the answers and only correct answers, but it might be an infinite algorithm and I don't know whether it has already found a solution or not. So I might have to wait infinitely long for an answer, which is obviously not a decision procedure. So the question is whether a calculus finishes in time is the theoretical notion that's called termination. And we can say that an algorithm decides a logic, so a formal system, if it is sound and complete and terminates. So that's a property about the calculus. And then we can extend that to a property of a logic. So a logic is decidable if it can be decided, if there is an algorithm that decides the logic. So a logic is decidable if there is a sound, complete algorithm that terminates. And that is, sort of goes back also to the story of yesterday. There are languages for which we can prove that no such algorithms exist. And in most cases, there are sound and complete algorithms, but they don't terminate. So you have in principle to wait infinitely long to get the right answer. But this is the most important notion in logical and computational logic. You're always looking for languages, expressive languages, for which you understand the semantics and for which you can write an algorithm that decides that language. Yes? No. If my algorithm gives only correct answers, it doesn't mean that it gives you all the correct answers, and vice versa. So if the question is whether a fact, I have a finite list of facts, and I want to check whether they are all entailed or not, I can give you an algorithm that simply returns all the facts. And it's a complete algorithm, because it gives you all the correct answers. But there are also incorrect ones in between them. So it wouldn't be sound. Yeah? Yes. Only if you claim on the one hand that you're sound, so you give only correct answers, and you give all of them, then you know that you're correct. because otherwise you might have too few or too many. And this is exactly the theoretical properties that we're talking about here. Yeah. So for every logic that you develop, because we are now using a well-known, well-studied logic like propositional logic, but as a knowledge representation person or a logician, you are also trying to find logics and algorithms for these logics. You're looking for logics that have decidability property, and then you want to find an algorithm with which you can calculate and assign semantic values to your formula. And how, so sort of the main, I think the main two approaches, fundamentally different approaches they are. The first one is that you look for models, you really try to produce the structures that correspond to models, and then you do enumeration or search in those set of models. Or you have a set of rules of which you know that the application of the rules is complete, and you try to find a new sentence by rewriting on your original knowledge base to find the formula that I entailed. So these are the two different types of algorithms that we are going to look into today. The first one is the one for searching for the models. And we have already started to do that with our truth table algorithm. So there is a very simple method for deciding entailment or satisfiability in using propositional logic by simply enumerating all the possible truth assignments. So you just take all the possible variables, all your propositional variables, you systematically assign all the values to those variables, and then you calculate which are the models of those, which are basically the ones that if you evaluate the knowledge base, you get a value true, and then you evaluate those of the formula you want to check for entailment, which are basically, again, the ones where you have the value true, and then you just check whether those four are a superset of the three models, and then you're done. It's a very simple algorithm that each of you could implement probably in half an hour. But as I said before, so that's the algorithm in principle. That's the one for satisfiability. I explained it now for entailment, but satisfiability is even easier. You just have to look whether there is a value true coming out or not, and the ones that are true are your models. And then your knowledge base is satisfiable. So the algorithm is really so simple as take a truth assignment. If you find one that makes the formula true, you return it as a model. And if you don't find one after looping through the entire set, you just return that the formula is unsatisfiable. It can't be any more simple, but obviously it has a big caveat, and that is, what is the problem with this algorithm? It's an NP-complete problem anyway. So the search space remains exponential anyway. Yeah? But the question is, how big is your problem? And it's a complexity problem, you're right. And as I said before, with 9 variables, with 8 variables we have to search through a list of 2 to the power of 8 different assignments of values. And I don't know how many that is, but I know that it's a lot. Yeah?
Is it also the depth of my search indicate that 8
yes, I think, yes.
To search through 8
yes.
levels.
Exactly, yeah. So the 2 is, if you go back to the tree search from last week, then this is the, so there's an intermediate step. So this is the branching factor, and this is the depth. Because the branching factor is between something being true or false, and then you have to check for all the variable assignments of a certain depth of the tree. An intermediate representation is, this is the number of truth values, so that is true or false, and this is the number of variables. Yeah, this is the number of truth values, and we have just true and false. And if you have 8 variables, then you get this table. And I think just a quick calculation. That's 24 squares, so it's about a million, a bit more than a million. Just if you have 8 variables. You can imagine that if you take more variables, you're really screwed. Yeah?
2 to the power 8 is 256, right?
Is it? Oh yeah, of course you're right. It's not. It's not that bad. It was. I thought it was. It was more. So 2 to the power of 8 is 256. 256. Yeah. Okay. But still, we're working with 8 variables, and if you have a real problem in the world, you have 50 variables, you have 1,000 variables, and it becomes absolutely untractable. So this naive algorithm, the dumb algorithm of just enumerating all the models, simply doesn't work. So, of course, we haven't had the first week for nothing. You know that there are ways of doing more clever search, and that can be a heuristic, that can be particular. If you do some kind of depth first, you avoid redundancies, you apply heuristics, then we can really do something here. And the first one is a complete system that always gives the correct answer. But there's also some incomplete local search algorithms. If the search space becomes so big that you cannot guarantee to look at all the models anymore, you might have an algorithm that tells you very efficiently, yes, I found a model, but maybe never be able to prove that it doesn't find a model. And these are very useful algorithms sometimes. So unfortunately, we don't have time to look at these incomplete algorithms, but I can tell you about one useful application for that. There is one technology that now produces plans in planning. Planning has been one of the classic AI problems. You have a number of things you can do. You have a goal to achieve, and the question is, what is the right order of all my actions to get to somewhere? So I have to make a plan to get lunch, and then give a lecture, and then immediately I have to prepare some other stuff, and so forth. What is the best actions to take? Obviously, this looks very much like a search problem. So this has often been defined as a search problem. But you can also model it in propositional logic and then do decision procedure by logical reasoning. But then the task is there a plan? And every plan would correspond to a model. And of course, then the task is to find one plan that's good, that works. So even if you might not find all the plans in the world, it doesn't really matter as long as you find one plan very quickly. So in that sense, you might be very well off with a correct but incomplete algorithm. Yeah? We're looking here at the more general cases where we really want soundness and completeness. So we're looking at the complete search algorithms that usually go back to Davis-Putnam, as they're called, but the real ones were developed by 4 people: Davis-Putnam, Loveland. And I'm trying to explain those algorithms, and these are also the algorithms that you should practice tomorrow in the, on Friday in the working groups. Before I can do that, I need another technical notion that I started to talk about yesterday, and that is a normal form to which you apply these algorithms usually. So in many cases, you can produce formula already in a certain syntactic normal form. Otherwise, you can translate every logical formula into this normal form so that your reasoner only needs to take care of this one specific syntactic format. And the syntactic format that we are using here is what's called the conjunctive normal form or the clause normal form. Again, this is something you need to understand and apply yourself. It's not difficult at all. But it basically means that you have to rewrite your formula into conjunctions of disjunctions. So basically, if you have a formula such as this one, A or B and not A or C, and not B or C, you usually abbreviate that as sets of sets, where each of the sets in the middle constitute a clause. That's called a clause. And on these data structures, you can apply your algorithms very efficiently. So basically, the first task of your process of decision procedure is to transform your formula into clause normal form. And how do you do that? It is basically a very simple rewriting procedure, starting out with your formula in whatever format it is, and then applying these 5 rules in the right order. Is there anything to be discussed plenary? But it's a bit noisy. No? Okay. So it's important that you apply the rules in the right order. The first one is that you just rewrite any implication into a logically equivalent form of the negation of the implicant and the disjunction with the conclusion. The second one is that you move the negations inward. So whenever you have a negation and a disjunction inside a bracketed, then you can turn around the operator itself and distribute the negations. And that works both directions, so you can rewrite a disjunction, a negated disjunction, into the conjunction of the negated conjunct, and the other way around. This allows you basically to get all the negations down to the atomic level. So now we only have, after applying this rule, we only have negation at the very inside of our formula. Just a negation, maybe multiple negations, and an atom, a propositional atom. Then we can distribute the conjunction outward. So if we have a conjunction, then we can rewrite it as the left-hand side disjunction plus the right-hand side disjunction and a conjunct between the two. And the last one is that we can now split the clauses that we have now achieved, get and write that back into the syntactic form of the sets of sets. So it's a very simple algorithm, just these 5 rules. There is actually one more, sort of the top more, is that if you have an equivalence, you have to rewrite the equivalence as an implication in both directions. But that's in principle all you have to do. Yeah?
I have a question about this. Is there any intuitive way of understanding what you're doing? Because if we have to apply this, then we just basically apply the rules without actually knowing why that is the case.
The question is whether there's any intuitive way of knowing what you're doing here.
Yeah, why you do it.
So why the individual rules are true is clear. So the soundness, I would say, is clear. So that is basically, these are logical equivalences that make sure that whatever you produce is exactly the same logically as you had before. So it's all correct. The other question is, why is it complete? Why does it always end up in a normal form? That would be your question in technical terms. And basically, I believe this can be proven. I don't know it out of the top of my head, but I believe it can be proven that this is complete. Because, for example, in the first 2 steps, you move the negations to the inner part. That's very important because the negations applied to a conjunction changes your structure of the formula completely. So you first get rid of the negations. First you get rid of the implication, that's easy, the equivalence, that's easier. So and basically after applying the equivalence rule, you know that you don't have any equivalences anymore. So this first step simplifies it because the type of operators reduces. And that holds in principle up to here. So here you can show that the number of operators reduces. After that, you can reduce the complexity of the negations because the negation get inside. You can reduce the number of negations. And then here you make sure that the negations are at that the disjunctions are at the inside. So here you produce your clauses basically. So that's some intuitive way of looking at it, and it can be proven that this is a complete method for calculating it. Yeah. So if you take the example from the Rumpus world again, then you see that we have a start with a formula. We apply the equivalence elimination that I talked about, which is not on the list, simply rewriting it by a left implication and the implication the other way around. That gives you this formula. Then you eliminate the implication with this disjunction, second step. And it's a simple rewriting process. So you have the beta here and the alpha here, and then you have the negated alpha and the beta here, and you get rid of the brackets if possible. And then you get the Morgan rule, as it was called. That's this one here, the Morgan rules, where you get the negation inside. And after applying this, you only have atomic negations. And then you apply the distributivity law, and then you get to your clauses. So it's always the same steps. It's very mechanical, as every algorithm should be. And you should just calculate a bit with those up and down, and you will be done. So it's very simple. It doesn't transform anything in terms of the meaning of the formula, but it makes it more efficient to calculate with it. That's the only reason why people do this in the beginning. And the good thing now is also that you don't have to write rules later, for example, for all the different types of formulae. Now you have only one type of formula that you have to work with, and that's a disjunction, maybe with negation or not. And that's not so, it's not so crucial now for the Davis-Putnam, but it's even more important for the resolution later. So take a sheet, not now in the interest of time, but do it later today. Take some example. Oh, I thought I had an example on the slide before. But that's the algorithm. Think of an example from from the working sheet, for example, and then apply these rules and see that you are capable of doing this. This is easy points to get in the example. Okay. And now we apply the first version, the most simple version of Davis-Putnam algorithm. And that is based on the assumption that if we looked at the truth table, there we looked at the complete assignments. So we had 2 to the power of n, of the number of variables, possible ways of distributing our truth values. So we had to look through all the possible complete assignments. And now the idea is, oh, maybe we can already stop our search if we only look at partial assignments. So here we have the assumption that we don't start with a full assignment, but we start with assigning values one by one to the variables and check whether we're still consistent. This is an algorithm now for satisfiability. So if we find a solution, we're satisfiable. If we not find a solution, then we're unsatisfiable. And attainment can be defined in terms of proof by refutation, as I showed yesterday. So this is now about satisfiability. And the algorithm is very simple. If the partial assignment, so you run the algorithm on a partial assignment, and it's a recursive algorithm. If your partial assignments make a formula false, then you return false. If it makes it true, then you return true. And if it's not decided yet, then you run it one level deeper, where you make one additional assumption on one of the predicates, the propositions in your formula, and you run the recursive call here. And if this one returns a true, then you return true. And if it doesn't, you check the other possibility, the other value. So how does it look? If you apply the algorithm on these 4 clauses, you start with the partial assignment where you say the value, the proposition A is false. So the algorithm here, if you look at it, it starts with assigning the value false first. So we assign the value false for A, and basically it checks formula is still true. There's nothing sort of violated so far yet. So we can take the next proposition and assign a value to this next proposition. So that's B. We again assign the value false to it. In our algorithm, we check whether we are still satisfiable. We are. So we go to the next variable and assign a new value to it and call the algorithm again. But now we have assigned A to false, B to false, C to false. That's the red in this graphic. So basically now we violate the first clause in our formula, so we know that this returns a value false. And our algorithm now says if we return a value false, then we have to apply it on the value where we assign the value true to the last variable to which we have already assigned a value. So that is to C. We assign the value true now, so the green one. This is assigning the value true. But unfortunately, we also now get a contradiction because now A or not C is violated and not true according to this assignment. So basically now we have managed to show that whenever you choose B to be false, then we don't find a solution. So we have to backtrack on B and assign the value true to B. Well, then we see already, oh, this doesn't work either because it violates this second clause in our set. So that means the choice of having A to be false was not a good one if we want to find a solution, a model. So we assign the value true to it. That works, no contradiction yet. Then we have to assign B, and that's the value false again according to our algorithm. That also still is satisfiable. It works, so it is correct with respect to our formula. So we have to assign a value C. If we apply the standard algorithm, say it's not C, then we get another contradiction because this would be A is true and C is false, would contradict this one. So we have to do some backtracking, and we find a solution with A being true, B being false, and C being true as a model for our formula. Yeah?
Is this that first search?
That's that first search, yeah.
But despite that they have a limited amount, a limited depth, that makes the algorithm complete.
Yeah. And obviously this is far less search than going through all the possibilities of these three variables. Of course, it still remains a sort of relatively big tree, because as we only have three variables here, the total number of assignments is only 8. So that's not too big anyway. And here we looked basically through many of those assignments as well. But it's already a big improvement as opposed to the standard truth table. I think it's time to have a break before I go on with the algorithm, with the improvement of the algorithm. Let's come back at past, and then we get through this.